I am Dr. Shriraj, Assistant Professor in the Aeronautical Engineering Department at MITE, Moodbidri. I am going to deliver a lecture on characterization methods to quantify properties of composite material. In the regular class, it is discussed characterization of properties. First three, that is density determination of fiber and matrix, as well as density of composite. And second one was fiber volume fraction identification from the composite. And third was tensile property of fiber, and now we will see continuation of that tensile property determination of matrix material. The test is carried out as per ASTM 638 standard. Usually dog bone specimen is used for performing the tensile test. The major parameter determined from this test are strength xm, Young's modulus em, ultimate strain epsilon mu. Here all these m subscript indicate it is property related to matrix. Also, to find out Poisson's ratio of the matrix specimen, strain gauges were mounted at the center of the specimen, where lateral strain and longitudinal strain are measured. The strain gauge works based on the principle that as deformation of the material is changed, the resistance of the strain gauge material, which is going to change. That is a measure of strain experienced by the specimen. For thin polymer sheet, flat specimen is recommended. You can see the difference between a dog bone specimen and flat specimen. In case of dog bone specimen, there is larger grip width that ensures that the stress is reduced at the gripping. And in case of dog bone specimen, because of larger width at the end, the grip region is strong. Whereas in case of flat specimen, the width is uniform throughout the length, so high stress concentration can occur near the grips, and hence the failure could be premature. The obtained tensile property is 2 less than the real value. Sometimes tab, which is made from steel or fiberglass, are bounded at the grip region for holding the specimen. Here LG refers to gauge length, LT refers to length of the tab, and capital T refers to thickness of the specimen. And for finding Young's modulus of the matrix, it is stress by strain. Here P by WT indicates stress and strain is epsilon 11m. 11 refers to on the loading rate. And the Poisson's ratio of the matrix is lateral strain epsilon 22m divided by epsilon 11. The strength of the matrix is nothing but the ratio of load by cross section area. Here the load is maximum load, we are going to substitute that indicate maximum value of stress, which is nothing but strength of the matrix, and the area resisting the force is nothing but width into thickness. The next characterization of property is finding tensile properties of unidirectional lamina, UD lamina. The recommended ASTM standard is ASTM D3039. In this standard, test has to be performed. Especially for finding tensile property of high modulus and high strength fibrous composite, it is challenging because there can be chances of grip failure of the specimen at the grip. The possible solution for this is to use wedge action friction grip. Here the wedge refers to it is V-shaped or triangular shaped tool which is designed to hold this wedge action grips. It is meant for holding the specimen and in the testing machine, and as well as for proper positioning of the specimen. As testing load increases, it ensures gripping force is higher, thereby ensuring that the specimen slippage is. The tab material could be made from steel or fiberglass, or sometimes a low modulus of elasticity material with higher strain, so that it should not take any load, but it is meant for deformation. You can see from figure 11 that tab material are adhesively bonded to the test specimen, and the thickness of this tab, that is TT, can be 1.5 to 4 times that of thickness of the specimen, which is T. There are two properties which can be found out using ASTM D3039. First one is longitudinal properties, the property along the fiber direction. For that, lamina with 0-degree ply, fiber oriented in 0-degree direction, having width 12.7 mm is. For finding transverse property, 90-degree lamina with width 25.4 mm is here. This specimen is loaded at a rate of 0.02 centimeter per minute. This load is steadily increasing with the time until it is failure. There is no reversal of load or no cyclic variation of load. Load is gradually increased, and that is applied in one direction. The longitudinal property first involves longitudinal Young's modulus, which is as same as the previous method, load by area that indicates stress. In the denominator, it is strain, longitudinal strain, and Poisson's ratio, which we call as nu1 2, which is major Poisson ratio. Longitudinal tensile strength is maximum load divided by cross section. We make use of 90-degree lamina, that is fiber oriented along x2 axis. So hence in the denominator, the strain used is used, strain epsilon 2 term is used. Test, that is from tensile test of 90-degree lamina, minor Poisson's ratio is obtained, that is nu q1, which is equal to minus epsilon 11 divided by epsilon 2. Transverse strength of the 90-degree lamina is measured as maximum load, which is along the x2 axis or 2 direction to the cross section area of the specimen. Sometimes for particulate composite and quasi-isotropic specimen, tensile test specimen may have dog bone shape. So for unidirectional composite, flat specimen with end tabs at the end is used. With the use of end tabs, stress concentration at the gripping region is reduced. Also, it confirms that the failure of the specimen would be near the middle of the laminate or within the gauge region, that is within this region, LG region, not at the grip. The obtained value will be a reliable one. Another method of characterizing the properties of composite is finding in-plane shear property. There are various methods available to find in-plane shear properties, like picture frame test, rail shear test, tube torsion test, plate twist. Especially these tests are used for finding property of UD lamina, unidirectional lamina. But the challenge with these methods is that it requires complex shaped specimen as well as specialized or custom made fixtures. Among all, off axis specimen which is subjected to tensile testing is the most shear property. It is nothing but we have specimen with fiber oriented at some angle to the loading direction, and we are conducting tensile test on such off-axis specimen to find the in-plane shear property. This figure 12 shows off-axis specimen with x1 axis indicate the reference axis x1 and x2, which is nothing but your 0 degree and 90 degree. X1 dash or x1 prime refers to fiber oriented along this direction. The orientation of the fiber is at making an angle phi with reference to reference axis. We call x1 dash and x2 dash as material axis. This off-axis tensile test specimen, we choose fiber oriented at an angle phi with reference to horizontal axis or x1 axis, and we conduct. Using this method we can find out in-plane shear modulus, that is G12. Equation 6 shows the relation between various elastic properties and constant. In this equation, to find the G12, we need to know longitudinal modulus, transverse modulus, and Poisson's ratio, as well as we need to know about M and D. Here, Young's modulus or E prime refers to that the property is measured along the material axis. Young's modulus 1 1, that is longitudinal modulus 1 1 without any prime, that indicates that the property is measured along the x1 axis, and that is again the ratio of stress by strain. You can here also notice epsilon 1 1, it is not epsilon 1 1 prime, right? That indicate these properties is a function of reference axis, not material axis. But the challenge with this method of determining in-plane shear property is that utmost care is required to perform off-axis tensile test, because there can be chances of coupling effect between normal stress and shear stress, or normal stress and shear stress can interact and cause additional lead to bending moment at the grip and shearing force at the grip points. To avoid this effect, one can choose specialized fixture which permit small movement at the end and reduce rigid clamping effect. Other option is to choose. Another method to determine in-plane shear property is to conduct a tensile test on a symmetric laminate with fiber or ply orientation plus minus 45 degree. This test has to be performed accordance with ASTM D3518 standard. Applied load, longitudinal and transverse strain are recorded until the material gets failure. Shear stress is computed using the formula or using the relation sigma 12 is equal to load divided by 2 times cross section area. Load is equally shared between plus 45 degree and minus 45 degree fiber, and shear strain is nothing but the sum of longitudinal strain, that is epsilon 1 1, plus transverse strain, that is epsilon 2 2. Now for finding shear modulus, we have the formula G12 is equal to shear stress by shear strain, and for finding shear strength, that is maximum value of stress, the ratio of maximum load up to failure to the 2 times width into thickness. Figure shows the specimen which is symmetric laminate with plus minus 45 degree, which is subjected to tensile test. Compressive properties of unidirectional lamina is determined using ASTM D3410 standard. Usually, when the unidirectional lamina is subjected to compressive test, as per this method, there can be chances of premature failure or early failure, such as fiber buckling, fiber breaking, or matrix shearing. This has to be avoided. So the method available is to choose a specimen of very short can see here compressive specimen. Load applied should be along the specimen center line, or your compressive load should be always along the axis. A Celanese compressive test fixture is used for conducting compression test. You can see here the shape is a truncated conical, that is grips are cone shaped with the tip cut off, forming a flat end. You can see inside these end fittings it is tapered, that is done to match the conical shape of the grips to fit inside. Taper design distribute even clamping forces on the specimen. Figure shows the compressive test specimen, and strain gauge is mounted at the gauge section to measure compressive strain. Compressive strength of 0° lamina specimen is computed using this formula. And for finding longitudinal compression modulus, again a load width thickness has to be measured, and it is nothing but stress by strain. Here stress is compressive stress, strain is longitudinal compressive strain. And Poisson's ratio is as usual minus of lateral strain, which is compressive in nature, to the longitudinal. Is the interlaminar shear properties of the composite is determined as per ASTM D2344 standard. Usually interlaminar refers to properties between shear moduli G13 and G23 and shear strength X13 and X23 are known as interlaminar shear property. You can see here the unidirectional composite where fiber is oriented or aligned along X1 axis, and X2 and X3 axes are mutually orthogonal to X1. The face which is perpendicular to the X1 axis, we call it as face number 1 or face 1. So in this sigma 1 3, the first index 1 refers to it is the face on which the stress is acting, and 3 refers to the direction. Second subscript refers to it is the direction in which the stress is acting, that is 3, X3 shear stress. And these two stress which is complementary stress, that is induced within the material because of the application of this. Sigma 23 or X23 refers to the stress which is acting on the second phase and directed in the third axis. The phase which is perpendicular to X2, it is the two stress, this stress and this stress, that refer to sigma 23, that is also interlaminar shear. Most conventionally used method is as per ASTM D2344 standard. With this ASTM D2344 standard, the shear strength only X13 can be captured. Two possible type of specimen can be used to conduct interlaminar shear test. First one is flat specimen and second one is ring specimen. Here the span to thickness ratio is very small, hence it is called short beam. Span refers to the length between two support points where you are holding the specimen, and thickness it is mentioned here as h, total length of the specimen to the thickness. Recommended is between 6 and 7. The test has to be performed at a speed of 1.3 mm per minute. With this test, you are going to find out X13, which is given by the formula 0.75 P max, maximum load, divided by B into H, width into. At the end of the material, the specimen is supported and load is applied at the center. This induces shear stress, hence we call it as 3-point bend. The data obtained using short beam shear test are not used for design purpose. It is only used for quality control and specification purpose. The major reason is, as the first reason is, short beam shear test results do not accurately represent true interlaminar shear strength of the composite. The main reason it could be limitation of test method and other factors. Test methods do not create even stress distribution within the specimen. Usually at the loading point and at the support point, the stress concentration could be more. as we are using very small size specimen for short beam shear test and of specific geometry that may not reflect the behavior of larger or complex structure. The loading condition what we follow may significantly differ from the real applications. So that's in such case the obtained value may be a lower one or greater than the true value. If this is your ILSS specimen, short beam shear test specimen, there can be crack formation or delamination. In this region, the fiber can bridge the crack. So as a result, it can artificially increase the measured strength.